afternoon, everyone. I'm Purva. We welcome you back to the talk sessions. We had two wonderful talks this morning, and with the same excitement, we will move to the next talk of the day. For this, we are pleased to welcome Dr. Tapan Chandra Adhyapak. Dr. Adhyapak is an assistant professor in the Department of Physics at the Indian Institute of Science, Education and Research, IISER Tirupati. He completed his PhD in the Department of Physics at the Indian Institute of Science, Bangalore. He then went to do his postdoctoral research in Germany, after which he joined his current position at IISER Tirupati. His group's interests lie in broad research areas of active matter, non-equilibrium statistical physics, driven soft and biological matter. Today, he will be delivering a very interesting talk titled 2-Minute Recipes for Model Building, a Daydream or Reality. We hope you will all enjoy it and it will be useful when you will build your own models. I request all the participants to mute themselves, and in case any of you have questions, you can leave them in the question answer forum or the chat box. Over to you, sir.
Thanks, Purva, for the introduction. And shall I start my screen, sharing the screen now?
Yes.
So let's see if it works. Can you see my screen?
Yes, sir.
Okay, so how do I? Okay. So how do I hide this portion? I don't know.
Sir, only the presentation is visible.
Oh, is it? So okay. So I have some small pop-up thing
Yes.
coming up. So you okay? Then it's great. Okay, thanks a lot, Purva, and thanks also to Srividya and Tejas for inviting me to speak here. So, by the way, so my presentation got stuck. Yeah. Okay. So I'm really delighted. I mean, so I'm glad to participate and deliver a talk among you. So I understand that so all of you are actually very good in science. And the topic that I'm going to talk about is, I mean, it's a quite vast topic, and the 2 minutes recipe here is a metaphor. I mean, so I just what I mean is that so nothing can be done in science in 2 minutes. I mean, so unless you're lucky in a very extraordinary way. So 2 minutes recipe is like the 2 minutes Maggie noodles recipe. So it's something that is I mean that you can explain to everyone mm, quite quickly, and everyone understands it, and everyone can follow it and implement in their own way and be happy. So something like that can it exist also for model building. So that's what we are going to discuss today. However, by the way, can you hear me?
Yes, sir. You're audible.
Okay, great. So it's been a long day already for you. So I understand that all of you might be quite tired. So I'm going to keep this talk quite light. That is rule number one. Rule number two is that I'll be because of that. I mean, so I'll be trying to avoid mathematical expressions as far as possible. I have kept only one or two, but I will not be certainly explaining them. Okay, so just to show that there is something. So other than that, it's mostly just a talk thing. And I mean, my feeling is that most of you actually know what is there, but you kind of want to uh, listen to others. I mean, so somebody who is little bit experienced in this field. Okay, that's so I'm mostly I'll be actually kind of motivating you. Okay, so then let's start with it. I mean, this is the model of the talk. Okay, so this is how I model my talk. Okay, so it's very simple. So first, introduction to the modeling, then abilities needed to develop the models, and then how to build models basically. Okay, so that's the model. But wait, this is a crude model. I mean, so I have just put very few objects, and this is where I uh, started with. But then now that we have a crude model, we can actually build up a little bit and refine it a little bit. Okay, let's see how the refined model looks like. Now I expand its points here a little bit, then make it more meaningful or more specific. For example, in the introduction, I will talk about why specifically I am talking about modeling. Okay, then what are actually these models? So why we need them? I mean, there is a great deal of misunderstanding, misinterpretations, yeah, even among the, I mean, senior scientists. Okay, so I want to actually just give my opinion. So, by the way, in my talk, I will not be giving any kind of rigorous definitions. Whatever I give, this is like my view. Okay, and just take it lightly. So that's where I'll start, and then I'll talk about what it takes to build a model, and specifically, can you do that in your project, in your AIIM project? And if you can do that, then how should you approach? And specifically, is there 2 minutes recipe available? Okay, that's the plan. So let's begin. So first of all, I want to talk about why I am actually talking about modeling. So here there are two parts. First part is that why we are talking about modeling, and once we understand that why we are talking about modeling, then the second part is why it is me that is actually invited to talk. I mean, so am I like the god of modeling or champion of modeling, or a layman? So very much like you. Okay, so that's what I want to explain. I mean, so just as a cautionary remark. Okay, so first of all, why we talk about modeling? So as you know, all of you are aware. I mean, so modeling is very important for your projects, AIIM projects, and they have been important. Actually, they are important for any project, any research project. But for AIIM, actually, if you want to go ahead of your competitors, you need good modeling. Okay, so this is one of the criterias already set up. But this is more so this year. That is because of the COVID-19, the coronavirus thing. So I understand that most of you, when you have started, when you will start your project, so you'll be actually remotely working on it. Okay, and in some places, I don't know how long it will take before you can actually go to your lab and start working on it. So building on mathematical modeling and understanding the backgrounds and other things will actually be quite helpful, especially at the beginning, and you will have more time to be spent on mathematical model building this year. Okay, this is why specifically this year it's very important. Uh, and then why me? Because I mean, some of you know me because of my involvement with the previous year's AIIM team from our institute, IIT Tirupati, which eventually won a gold medal. And I mean, yeah. So the students, the participants, actually interacted with me for a part of the models they did. And because of this, I was actually approached to shed light on the following. So how to model AIIM projects. Okay. And immediately when I saw this, the first feeling that came to me, first reaction was this: if only I knew, okay, how to do it. Okay, so I mean, it's absolutely it's a valid question, and it's a very important question, and I'm sure all of you want to know it. Okay, how to model AIIM projects, but at the same time, it's actually very hard question to answer. For example, it's very similar to the question like how to be happy in life. Okay, this cannot be actually told in general, uh, at least by person of my experience. So for people who get kind of enlightenment or many years of experience, they can actually try to say something about it. Okay, but I would not dare to do it. So immediately, soon after that, actually, I got a clarification that no, actually, I have to actually clarify on specific questions. And the questions are like how to start developing a model. Second was how to determine the relevant parameters required for developing the model. Okay. And another one was how to check if the attempted model is the correct one for the project. Okay. So I got these clarifications, but when I reflected, I saw that, okay, so these actually did not help me much because these are also very tough questions to answer in general. Okay. And if I know the answers of this question, basically I sort of know the answer of this question. Okay. So, so what I thought then is that, okay, so because I understand that these are all valid questions and all of you actually need to know at least some general way to do it. But with the little experience that I have on model building, by that I mean that I have only few experiences. Okay, so it's actually literally true. So I can actually give my views on these points. Okay, so that's what I'm going to do it today. So whatever I will be giving, so this will be like my views. These are not the general recipe or general laws or rules with which you should actually approach. And one small disclaimer. So as Purba has pointed out, actually I am not a biologist. I mean, so I am by training I'm a physicist and I work in theoretical physics. Okay, so I know very little of biology, and also I know only as much physics as it helps me to survive. Okay, I don't claim that I know a lot in physics as well. So with this, whatever the view I'll be actually explaining to you today, those will be subject to this kind of constraints, okay, of my knowledge and experience. So the cautionary word is don't go by my words, go by what I mean to say. Okay. So by that again, I mean that I'll be talking about specific examples at the end. Those examples are taken from the examples that I have experienced, and I will try to generalize few points out of those. Okay, but those may not fit directly word to word to your project, but if you can translate it, so the meaning, translate the meaning, and then try to fit it into your project, then you'll, I'm sure you'll get something out of it. So my hope is that if you follow this sentence, then actually uh, my hope is that you will get something out of this talk that will be useful for you. Okay. So then, so I start with by explaining what are models. Okay. Again, before giving a rigorous, so I don't give anyway rigorous definition, but before giving any kind of definition, I just wanted to give a story. So tell a story. So, so this is an experimentalist who observed a particular phenomena, a parameter y, as a function of x, and found this plot. Okay, and he was quite puzzled by this. I mean, why it's going on, why it's happening, he didn't know. So he wanted to understand it. So he approached this smart and confident theoretist. Okay, so he's a model builder. Okay, and he showed the experimentalist showed the plot to him. The model builder said that, oh, okay. Then he, the model builder took it. The theorist took the plot to his home. Overnight, he worked on it, and the next morning he came back to the theorist. As soon as the theorist saw him, the theorist wanted to say, so the experimentalist wanted to say something. Okay, but the theorist actually stopped him, and he was actually quite confident and very excited. And he said, okay, look, I have perfectly understood how your system is behaving. And then this is my theory. I have developed a theory based on this understanding. And so the plot that my theory is giving is shown with this red curve. And as you can see, this is actually pretty much explaining your data. Okay. And then the experimentalist finally got a chance to speak, and he said, sorry, friend, actually, I forgot to tell you. I wanted to say you actually at the beginning, but it could not. Last time I did a mistake, and I plotted everything upside down. Okay, so the actual plot is this one. So here, instead of y decreasing as a function of x, it is actually increasing. Okay, so that's like the oops point. Okay, so because the theorist said that he understood everything, but then looking at this new plot, the theorist was still calm. I mean, so he was unfazed by this new development. He said, "Okay, okay, give me the new plot." And he took away the new plot and he went back. And next morning he came up with a new story, new theory. This is the new theory. He said, "Look, my friend, I've got the new theory, and it explains perfectly well your data. So this is the theory. This is the understanding of your system." Okay. So these, probably you have heard about this joke, but this joke is quite a bit often. I mean, so to make fun of theorists. I mean, it's a bit funny, of course, but I'll come back to this point, and I have few other jokes today to share with you. But to each joke, I have actually some message, okay, which actually tells you something about model building. Okay, so I'll come back to this later. So then before that, I mean, so let's get a little bit serious and see what are models. So a model is a representation of a system. Okay, that so the represent so some form of representation, and with the representation, we can actually understand the system and also quantify. Okay, so I'll soon give some examples, but just now you just know, it's sufficient to know that there could be two different kind of models. One is a conceptual model, which describe the system in a qualitative way, and there is a mathematical model, which describe the system in a quantitative way. Okay, and I'll actually show that for a mathematical model, we actually need the conceptual model first. Okay, so here is an example of conceptual model. So I mean, so this is this typical example of this cell. Okay, so it's a drawing, of course, it's a sketch of this cell, and it's based on many different observations made on different parts of the system, parts of the cell, with various different experiments. Okay, and the model kind of integrates everything, all the knowledge, into one unit, and actually tells you what is the cell as an entity. Okay, what are the different components. The nucleus is located somewhere in the center. Okay, and their mitochondria and other stuffs are working, so they could diffuse, and so and so forth. So this is a model, but everything, as you have seen, it's actually explained in a qualitative way. So there is no quantitative measurement, nothing here. Another example is this reaction pathways. Okay, so I took an example from biology because most of you are biologists, but it could be for any chemical reaction. So it's a pathway is actually kind of correlate a series of reactions. Okay, so here is an example of reaction happening between two substrates, and the enzyme is acting like a catalysis. And as you can see, the substrate actually attaches to the active sites of the enzyme, and when it does so, the shape of the enzyme changes, and then there are reaction products, and these are actually so depicted by this model. Okay, so this happens, and then this happens, then this happens, and so on and so forth. But again, it's also a qualitative measurement. So you don't know how much energy is needed to bend the enzyme. Okay, how much time is needed between these two steps, how much reactant is needed, what is the probability of red molecule to get bind to this side. Okay, so those are a kind of some kind of quantitative measurements which are not present here. So then let's go to the mathematical model. So here, those quantifications are obtained, okay, by using some kind of mathematical representation of the same system. Okay, so basically you will have equations or expressions and so on, and from that you can find out quantities that you can actually measure, that quantities with which you can validate your system most importantly, once you know the mathematical model or the understanding, you can actually predict things that you have not already measured. Okay, so this is the most powerful thing of mathematical model. And then for physicists, the most attractive point is that the mathematical model gives you an understanding based on the very fundamental laws. Okay, as a physicist, we always start with minimum number of fundamental laws. Okay, and then anything that is observable, we want to link to those fundamental laws, and that we can do by using mathematical models. And in this talk, we are actually talking about mathematical models. Okay, but we will see that conceptual models plays an important role. By the way, you can all who are interested, you can look up this review article. This is a modeling. It is a review article on modeling in biosciences. Okay, it's a very nice article. And if you're really feeling like aimless or something, just go there and then you'll see. I mean, so whatever I'm going to talk, so they have talked much more than I have done. Okay, so so let's see some examples. Okay, so first of all, I'll talk about some different kind of mathematical models. So first of all, let me talk about curve fitting. Again, for some theorists, curve fitting is not a model. Okay, mathematical model, but for it's my view. I think it's a good starting point. And you know what is curve fitting. So I have some experimental data. These blue dots scattered all over, and the aim is to fit one smooth curve. Okay, that represents the data in the most suitable way. Okay, and you know what do you mean by fitting. Okay, once we do that, basically we get an expression for this variable y as a function of this variable x. Okay, here in this case it's an exponential variable, exponential function, and you can see that there are two unknown parameters, this a and b. They are obtained by fitting the curve here. Once you fit the curve, the values of a and b are known. Once the value of a and b are known, we know y as a function of x, and that's a mathematical expression, right? This is a mathematical model. But only thing is there lacking here is that this model is not based on some fundamental physics laws. This model has not been derived from that. Okay, but still, if your fit is good, then even if you derive the model from a fundamental law, you should end up on the same expression. So this way, this expression actually helps us to develop a actual theoretical proper theory that relates this expression to the fundamental equations. I'll have a solid example for that. Okay, later. So here is another example. It's a slightly different data set, and what is fitted is a Gaussian plot. Okay, and the expression is here. So you can see that there are like slightly more number of parameters, unknown parameters, and also different parts of the data sets are agreeing with different accuracy with the fit. For example, here we see some wave-like phenomena for the data set, which is not captured by the red plot, the red fit. So this is something that you always have to actually think about. So whenever you are plotting, just concentrate, focus on the most relevant part and try to fit in that part. The other parts might actually deviate a little bit. By the way, if you would have actually chosen only this part to be fitted, then you could have also fitted a straight line here. But of course, straight line is not a good representation for the data set, right? So whenever you see a data set, first, from your experience, you should actually guess what kind of mathematical form it could be, okay? And then you start fitting your data. So that is one lesson that came out of it. But another lesson that is actually, this is a statement, it's a famous statement, probably, I don't know whether you know or not. And he is a physicist and mathematician and also computer scientist, John Newman. So he said that with 4 parameters, I can fit an elephant. And with 5, I can make him wiggle his trunk. Okay. So what does he mean by that? By this, he means that, so if you take a complicated enough expression, like even more complicated than this, with many, many parameters, you can actually fit anything you like. Okay. So suppose you have a very different kind of curve in a data set, and somebody comes up with a very complicated expression. Okay, and he fits the data, he will perfectly fit your data, but then he can actually parameterize his model to fit anything else as well. So that model is not uniquely expressing your data point. This is not a good model. This is what is meant by that. Okay, so a very complex model with many parameters can be fitted can be actually parameterized to fit anything. But actually, some people took it quite seriously, this statement. And it turned out that actually elephant with 4 parameters can indeed be uh, parameterized, provided those 4 parameters are actually complex numbers, which means that actually we have 8 parameters, basically minimum 8 parameters in it. And there is actually serious paper. This is the paper. You can look up here. And so it's actually a kind of respected journal, international journal. And also you see that this is published in 2010, not many years ago, just 10 years ago. Okay. And what they have done, so they did, this is the data set, reference data set. Okay, so this is what they wanted to build. And they have a mathematical expression with 4 complex numbers. With that, they fitted the elephant. As you can see, it looks like somewhat like an elephant. Okay, and also it's wiggling its trunk. Okay, so people do take these things seriously, and then you can do many things with complex parameterization. Okay. Okay, so so here comes the example of curve fitting. This is an example where just by inspection you can see that this data set is more or less falling on a straight line. So it's actually valid to plot fit a straight line. But what about, so this is an example from biology. Okay, so these are E. coli, okay, swimming near a substrate, and these are actually their paths. And you can see that the E. coli are actually moving in circular paths near the substrate. Okay, and this is observed in 2006, and people were kind of puzzled. I mean, so why it's happening? Why they are swimming in circular paths? Because when they swim away from the substrate, they swim in straight path. Okay, so first they made some measurements. So as you can see, this data set is actually the radius of this circular paths as a function of the cell size, cell body size. And they have this scattered data. It's all of them is scattered all over, but still probably still can see a bend. So they tried to fit a straight line. But look at this plot. Okay, so here the swimming velocity is plotted as a function of radius. And here I don't even see a bend. I mean, so there could be a point here, just because of lack of experimental data, it's not there. So one point here, and then you'll get a totally different straight line, something like that. Okay. So how valid is this straight line? So they still nonetheless fit the straight line here with this data. So it turns out that this fit is a guide that I told you. Like when you fit something, you get an expression, and that gives you a guide to develop the proper theory. And these people, Lauga et al., they developed actually a proper theory of a very detailed mathematical theory of bacteria swimming in a fluid. So there is hydrodynamic interaction, there is interaction from the substrate, and everything is there. And they came up with a theory, proper theory, and then when they solved the problem, they got almost, so these data points are from the theory. Okay, so they're falling on top of the fitted straight line. So the moral is that the fitted straight line is hello, hello, can you hear me?
Yes, sir.
So sorry, there is a power cut in my building, so I'm using hotspot. So can you see my slide now?
Yes, sir.
Okay. So basic moral is that whenever you have I mean, this kind of clumsy fitting, then you can actually take the help of that fit and then develop some theory. And if the theory actually agrees with your fit, then you are actually more or less done. So this is a good. Then you can say that it's a good theory. Okay. So let's talk about some other types of models. So there are static models which describes quantities or properties of the system which are time independent, like the structure of the system, the equilibrium condition, of the systems, so and so forth. There are dynamical models. Okay, so dynamical models tells you how properties of the system is changing as a function of time. So here is an example of those equations. So a quantity x1 is changing with time. So there is this dot here. So how it's changing with time? It's actually coupled to other parameters x1, x2, and so on. But this x1, x2, they have their own dynamics. So for example, x2 has the dynamics of its own. So basically, it's a coupled set of equations, and it's a dynamical equations. And this one is particularly is an example of nonlinear dynamics. Okay, and if you don't have any randomness in the system, it's a deterministic dynamics. And just remember this term, nonlinear dynamics. It's actually many biological problems fall into this category. You can actually explain using the techniques of nonlinear dynamics. And if you have randomness in this system, then you can have diffusion, you can have reaction diffusion. These are also very common processes in biology. And many different biological systems can be described by equations describing diffusion and reaction diffusion. Okay, so these are some key techniques that you should look up when you are actually trying to find some model for your system. Okay, there are other models. This is a phenomenological model. So what is a phenomenological model? It's a model that is to some extent built on the basic principles of physics. Okay, but at some point you are stuck. You don't know how to proceed, and then you look into the experiment and you see what is observed. Okay, and accordingly you change. Okay, and then you incorporate a term. So basically, you incorporate a term in your equations so as to reproduce the uh, experimental observations. So it's experimental phenomenology. That's why it's called a phenomenological model. And I mean, at the beginning, you started for an explanation. So you wanted an explanation for the experiment, and now you are building your theory to reproduce the based on your experiment. So it doesn't help that way, right? But actually, this is very important in the sense that once you actually incorporate the phenomenology into your system by hand, okay, not by basic principles, by hand you put it, but then you have a basic structure of the theory, and with that we can explain many other things that is not observed. That is the power of that phenomenological models. And the example that of this theoretist producing theory for both the correct figure and also the upside down figure, okay, is an example of phenomenological model. So phenomenological models are based on experimental observation. You give me the observation, I'll give you the theory. Okay, so in that sense, this joke is not a joke actually. It's a very powerful tool. Okay, then let's talk about so what it takes to build a mathematical model. Okay, so let's see what is it. I mean, so I just have a schematic here. So this is a bullseye, and this is the target. Okay, and let's say this is your experimental data, the black dot, the blue bullseye. Okay, and you want some theory to explain that, and then you approach the same confident theoretist. Okay, he has some tools, and this is the theory or equations that he knows, and these are the solutions of those. So all he has to do is to aim the theory, basically take the proper theory and equations and take proper solutions so that it hits the bullseye. And if he is an very experienced theorist, he can do it right away, directly hit the bullseye. Okay, but things don't work that way always. So for beginners, you can actually not beginners, and depending upon problems, you may not find a answer directly. So what you can do, you can have an approximate solution, which is actually kind of explain your data, but approximately. And then you can go on adding more and more complications to your theory so that the answer improves. So this is the general pathway that we are going to take, and then I'm going to explain with some examples. Okay, but before that, let's see another example. So this friend here is a very confident guy, and he has this funding and other things, so he knows his bullseye. But here is a poor guy. I mean, so he doesn't even know his target. He has the bow, and he knows some equations, but he doesn't know the target. But then some deadline came and some pressure came, and he has to produce some results. What he did, he just threw the arrow into the air, okay, without knowing any target. So once you do that, of course, the arrow will travel and ultimately hit the target, and it hit the ground, but there is no target here, okay. But then this guy, he got an idea. He just went there and then drew a bullseye, okay. Now he says that, okay, this is the target I was actually aiming for. And when he writes the AIIM report, like you on a deadline, he said that, okay, this is our data. And to get this explanation, I started with this theory, and I actually solved this in this approximation. I got this answer. Okay. I mean, this is how many people do it. But of course, I don't advocate for that. But interestingly, although this is again a joke made on theorists all the time, but it is actually something that is done by most of the theorists all the time. Okay, this is an abstract problem, and theorists like abstract problems. They like to solve problems because they can. Okay, they need not be there as a target. Okay, so they keep solving problems, and then they keep hitting the ground, and everywhere they hit, so ultimately the ground is full of this bullseye. And when a guy like you come to the field and then you get a data, basically it's more likely that although your data is target is new, there could be always theories that is actually hitting somewhere nearby. Okay, so basically some theories might be there already in the literature. Thanks to this guy, basically, or the theories like this, there is a available theories whose solutions are very near to what you want. Okay, this is something I want to actually use tonight. So I'll again come to this point later. Okay, then there comes this important thing, and this is again a fun made of so joke of the theorists. It is said that, okay, so the theorists said that let's assume the cow is spherical. Okay, it's actually a simplification for theorists, but it's oversimplification for others. Okay, so just to have an idea how overly simplified is this, if in case you don't know, cow looks like this. Okay, so it's nowhere near a sphere. It has corners, and here is corner, there is a corner, there is a corner, long of protruding things and other things. Okay, so it's a drastic change, but we'll see how powerful is this. Okay, and even though it's a joke, but it's actually very powerful tool for theory. So now the point is, can you develop a mathematical model? So you, meaning the participants of AIIM and other things. Okay, and this is a quotation actually expressed to me by my master thesis supervisor. Okay, I still remember it, and it changed my life a little bit. Okay, I was struggling with something, and I actually said that, okay, he knows many things and much more things, and his ability is much more than myself. Then he said that no, the difference between you and me is just the experience, not the ability. Okay, I have more experience, more number of years of experience, but other than that, I don't have anything special. Okay, that kind of change boost my confidence, and I believe that, actually not believe, I know that all of you are actually much better than us when we are at your age. You are actually the next generation people. You are actually, your abilities are actually much better than ours. The only difference between you and me is the experience. Okay, so yes, you can certainly develop mathematical models. Just believe in yourself. There are simple strategies that you have to follow. So I'll talk about a few. Okay, but so this experience thing that you can actually brought to your side by talking to faculty members or senior members who are actually experienced. Okay, that you can do, and also you can boost your ability through collaborations. Okay, so these are the techniques with which actually, if you follow this, then you can certainly develop mathematical models of your own. Okay, so then here comes the most important point, which all of you want to know: how to approach. So in my view, first you have to actually conceptualize. Okay, so let me try. My power has come, so let me try connecting to the Wi-Fi. Yeah, I think it's up. Okay. Okay, so this is the first step. So whenever you have a problem, try to actually verbalize. So say it in words, organize your thoughts. Okay. So when you organize your thoughts, you have to actually find processes that is actually going into it. Okay. So do it again and again. So that is the first step. So this is the conceptual model that you need. Help to find any processes that are going on, and also helps to find you some questions. Okay. So then once you have the conceptual model, so just assume the cow is spherical, which means that just look at the bare minimum important processes. Okay, so not, you cannot look at all the processes at the same time. So you have to look at only the important processes at work. So once you figured it out, so yeah, then you can go back to literature survey. Okay, so you know what are the important processes by so according to this spherical model of the cow, and go back to literature and look for available techniques or equations, analogy from physics and chemistry, and if possible at the end. So once you have done it, I mean, so once you have worked on it, if possible at the end you can add corners. Okay, if possible, to make it more realistic. But I will come to this list. I have more points into it once I have explained this some points to you more. But remember that most important step is this. So to get the bare minimum model, okay, and that has to be a spherical curve because it is actually the minimum. Okay, I'll show you some example. By the way, Purva, can you tell me how am I doing with time? Can I take
Yes,
5 more
sir.
minutes? Okay. So yeah, I'll try to wind up in 5 minutes or so. Okay, let's see. Okay, so this is the most important step, and uh, also it's the in a way it's easiest, but because you just have to think, but it's actually in a way it's very difficult as well. I'll show you. So here is an example from my work. So it's an E. coli. Okay, it's so you know this big bacteria. It's moving in bulk fluid. It has many flagella. It has a cell body, and its dynamics is quite complicated. Okay, and why we are interested in it? Just look at this collective dynamics. There are many bacteria here. Okay, it's a very dense suspension of bacteria, and although you cannot observe by naked eye, but there are very interesting flow patterns going on here. Some synchronization is also going on. Okay, and this has to come out from individual swimming pattern. Okay, so this is quite interesting, not explained fully yet. So we want to actually develop some kind of model for E. coli with which we can explain this phenomenology. Okay, this is our purpose. Okay, so how do we proceed? So first we have to conceptualize, meaning that, so by conceptualization I'm so we'll see what are the processes that are very important. Okay, and then we see the self propulsion. The bacteria moves of their own. Okay, they don't need any external force. They can move like move like us. So it's a self propulsion that is important. Because they're moving in water, hydrodynamic interaction is important, and hydrodynamic interactions will affect each other. Okay, because I'm looking at a dense suspension, they're bound to be affected by hydrodynamic interactions. Also the size of the cell body can matter. Okay, this is the conceptualization. Okay, now I have got some keywords: hydrodynamic interaction, self propulsion. I can type in Google, okay, to find something. Okay, now comes the cow part, spherical cow part. Now look at the bacteria. So it's like almost like a realistic bacteria. So how it moves? So it has this flagella. With this flagella, it pushes the fluid backward. Okay. So this is the fluid around it. It pushes the fluid backward. Okay. And like when you swim, we push the fluid backward with our legs, and that puts a thrust force on the cell body. Okay. These small forces are acting on the fluid, and this force is acting on the cell body, and the whole body moves in that direction. This is the realistic thing that is going on. But here is our spherical cow. So this is quite complicated to solve anyway. So very complicated object. This is flexible object. So instead of having this, we just have a point force, okay, here on the fluid, and it has the same kind of qualitative effect. It says that, okay, this point force is imagine a flagella here. Okay, this point force is generated by the flagella, and with this point force, the bacteria is pushing the fluid backward. Okay, as a result, it's getting a force on the cell body, And also the cell body is actually a sphere. Okay, it's literally a spherical cow. Okay, but for E. coli, it has to be an elongated object. But anyway, it works. And now, because of these keywords, I can search in Google. So okay, and I can see that okay, there are equations which actually gives you the solution for flow field around the swimmer. And if I know the flow field, I can actually calculate the hydrodynamic interactions. And I won't go through the detail, but this is the result of our calculation by solving this equation, solving this model. And you can, these are the flow patterns around it. So you can see the flow is coming and going this way. Okay, this is the swimmer, it's traveling in that direction. But look at this. This is something measured from an actual E. coli in an experiment. And look at this too. So you can see that the qualitatively we have regenerated the flow field. So the flow field is actually turning here, and there are four turning regions around the swimmer. Similarly, there are four turning regions here. You can see that with this spherical cow, we have actually generated a very nice agreement with the experiment. Okay, and with this we can study the collective behavior. And if you're really interested, we can actually add more corners to the spherical cow. Okay, this is also what we have done. And see, with these corners, you can get this elongated object, you can get many more flagella and so on. Then it's a very realistic model. Okay, you can, but these are done in steps. We start with that and add another thing, and then add another thing, and ultimately arrive at this. Okay, this is the way we. So then let's talk about another example. This is the example from last year's AIIM team from either telepathy, and they were studying drug-carrying E. coli, and they were supposed to carry drugs to tumors which are situated on the walls of human colon. This is a human colon. Okay, there are fluids around it. Okay, definitely it's a very hard problem to solve. Okay, so somebody who doesn't know physics, I mean, so you will be really scared. Even so, you will not know how to proceed. But on the other hand, if a person knows too much of physics, then it's a trouble again. So because it's a very complicated system, you have colonic fluid flow traveling here. You have this surface which is actually wiggly. Okay, and moreover, the surface is not static. It has peristal. It is actually peristaltic vibrations. Okay, going on over the time, and it's a hell lot of a complicated problem. But the students, the participants of 2019, they were in between these two spectrum of very knowledgeable physicists and not knowledgeable physicists. Okay, I'm sorry, my internet is really fluctuating. Okay, so they actually, this is the spherical cow they thought of. So they replaced the whole column by a straight cylinder. This is a straight cylinder now. Okay, and smooth cylinder, not changing with time. And then assume that okay, the bacteria have been released at the center of this axis of this cylinder, and there is flow, of course, and then how it's actually moving in the colon. That's what. So this is basically certainly a drastic simplification, but then we can actually figure out two important processes. One is diffusion, and the other is advection. So bacteria, because of the thermal noise, it's actually diffusing. If you start release the bacteria here, so they will actually diffuse through the width of the channel and will try to go to the boundary. Okay, this is the diffusion happening in the along the width. And also there is advection, meaning there is fluid flow because of the colonic fluid along the axis. Okay, if you just take into account these two factors, then what you can see, so when the bacteria is actually diffusing, so just imagine a bacteria diffusing from this center to this wall, but it is not diffusing at the same position because of the advection is actually going in this direction. So it is somewhat traveling in that direction like that. Okay, then you can actually find the distance Zi before which the bacteria cannot reach the colon. Okay, and with just simple these two concepts, this is the spherical cow. If you just search the theory, and then you can solve a very simple theory to come up with an expression for Zi, and that is actually connected to a parameter. Okay, that is connected with the bacteria, and it turns out that this parameter already tells you a lot. The parameter already tells you a lot about the bacteria. Okay, I need to actually hotspot. Okay. So it tells you that you have to take the diffusion constant of a motile bacteria for a realistic system, and also you can incorporate peristalsis. Okay, but that will change this diffusion constant. Okay, already with this simple assumption, you have these inputs, and then you know what parameters to actually look for, because your expression has this parameter, and you wanted to know the value, and we got this already, this insights. So we can go a little bit further. Basically, you can randomize the point of release here, okay, and then see what happens. So that's like adding the extra corners. And again, if you have the equations ready, you can just solve it. Just look for this point, and then you found that okay, that actually did not matter much. So once, so this is kind of already a win-win situation. But then once you have this whole mechanism ready, you can actually dig further. Okay, so you can get lucky, or you might actually spend more time. But once you have invested, why don't you actually try to gain the profit? So it turns out that by digging further, we could actually solve the same equations in different perspective to get different solutions. Okay, so for example, we could get the maximum concentration arriving at this point as a function of the concentration released here, which is quite important, okay, to for the drug delivery system. And also, we could figure out up to what length the bacteria can actually target a tumor. Okay, there will be maximum length ZF. So all these parameters were actually derived from this simple theory and the extra corners that you have added to them. Very simple, but they give these expressions in terms of parameters that are measurable in terms of our system. So we can go back to our system, we can measure this value of Zi, whether our model is actually accurate for or suitable for us or not. For example, at the beginning, we are using a diffusion constant for non-motile bacteria, and we came up with a very unreasonable number for Zi. Then we thought that, okay, no, something is wrong in our model. What is wrong? We have to consider motile bacteria. That's a good information. Okay, so with this, I come back to the original list. These are already talked about. You verbalize the process involved, and then use a very simplified model, and then search for equations, okay, available from physics and chemistry, and then find out parameter values which are actually needed for the bare minimum theory, and all those parameters are essential. So try to look for the experimental values. If some of them are not available, then you have to actually find a range from your theory, okay, which is allowed, and then look into your system whether those range is actually valid for a system or not. That will validate your model, and then you can actually try to extract as much results as you can get. Once you get it, then you can dig further to a little bit expand a little here and there, add if possible, add more partners. Okay, so yes, this is the kind of 2 minutes recipe that you can think of, but it's actually too vague, so we have to really think how to actually apply this to your own system. So with this, actually, my talk ends. So I can keep this list, and then I can take up your questions if there are any.
Thank you, sir. It was a fun talk, and at the same time, it was very informative. And most importantly, you started off with the basics and with all the images and animations. I'm sure even people who are not into modeling would have understood almost all of the things that you have spoken. So we have one question in the chat box. I would quickly like to take it up.
Mhm.
So the question is, if we have a plot and don't know which one fits it perfectly, is there any method to know the best fit equation apart from just checking all the equations one by one?
So no, actually, there is no general rule. Okay, so uh, okay, there is a new technique coming up, which is the machine learning. Okay, with that, you can tackle some kind of data set. So there, even if you don't know the pattern, the underlying pattern, you can actually come up with uh, some some answer. But that applies to only few specific sets of data points. But in general, there is no so you have to think about the mathematical model first. So that requires some experience, background experience, some knowledge about curve fitting and all that. Or what you can do, you can actually use